Hi, we are Team DiagnosNext, and this is our final design for use video. For this project, we decided to focus on how Georgia Tech laboratories need more efficient, cheap, and durable testing components to improve COVID-19 surveillance testing processes. We first tested several prototypes. The first was a plug or stopper lid. Unfortunately, the stopper lid was unable to be tested due to the limits of the printer. The second was a lid protrusion. It was determined that the test tube protrusion could have saved the COVID lab team a total of 19 hours by using the protrusion to break through the plastic bags. The third prototype is a drill-like device that can screw and unscrew test tube lids. It was found that this prototype can save the lab 3 minutes on each rack of 48 test tubes. Our final prototype is the ring loader. By using magnets, the ring loader can lower the time to load the mechanical disruption machine from 90 seconds to load to 2 seconds. This reduces the time by 97%. Because of these test results, we decided to pursue the ring loader as our final design concept.
This is our fusion model of our prototype, showing a ring loader that can gather 48 test tubes in the correct orientation to be loaded into the mechanical disruption machine. Our looks-like prototype is a speed loader. This is a handle component attached to a loading component that can gather and keep multiple bullets in the correct orientation. Our works-like prototype is this crane with an electromagnet that can attract, pick up, and hold large objects, such as cars. In our case, we would be using magnets to pick up test tubes.
6 requirements of good design. First, it does the job. It is able to reduce the amount of time needed to load the mechanical disruption machine. It does this by a factor of 48 by loading 48 test tubes at once rather than one. Next, it does make sense to the user. Due to the handle on both sides, it is intuitive for how to grip the magnet loader. Additionally, there are nests for each of the individual 48 test tubes, which makes sense to how the test tubes are connected to the ring loader. Next, the user can access it and the user can afford it. Because it is made out of simple materials, such as cheap magnets from Amazon and plywood, it is very accessible as well as affordable. Next, there's a system of proportions. Due to the symmetry of the handles and the equally spaced magnets on the ring loader, there is a system of proportions in this design. And lastly, it has an acceptable appearance. Because it demonstrates the 5 other requirements of good design, along with the symmetry and equal spacing, there is an acceptable appearance.
When our team entered the concept development phase, we explored a breadth of possible solutions while keeping user feedback in mind. All solutions were focused on making a more efficient, cheap, and durable testing component for the asymptomatic surveillance testing lab. While ideating, we focused on bottlenecks in the process that were specifically identified by the user. These bottlenecks include punching tubes out of the bags, unscrewing and rescrewing test tubes, and loading the mechanical disruptor. These problems are a few examples of the concept problems we focused on while ideating. From there, we were able to create concepts of many ideas to improve these processes. We looked into adding protrusions on the tubes, creating a motorized drill, and even a preliminary ring loader design. Individually, we came up with potential concepts that address each concept problem. This phase helped us brainstorm many possible design avenues. With feedback from our peers, teaching staff, and users, we were able to narrow down our concepts. Here on the screen is a concept drawing of a tube protrusion to speed up the process of punching tubes out of the bags. This is a preliminary drawing of the test tube unscrewing drill, which would speed up the process of unscrewing and rescrewing the test tubes. And lastly is a preliminary drawing of our magnetic ring loader. After deciding which concepts to move forward with, we started to physically prototype each concept. This was useful to gauge user feedback and test whether our idea would actually solve the problem. This is a prototype of our test tube protrusion, which we 3D printed. This is a looks-like prototype of our motorized drill, and this is a preliminary prototype of our ring loader, which we laser cut. Like Sarah mentioned, each of these prototypes gave us test results which helped us create a new iteration of the prototype. Combining these results with user feedback helped lead us to our final design concept.
This week, we were able to go back to the lab and talk to some of the lab personnel about their thoughts on each of our concepts. First, for the lid protrusions, they said this was a good design, but they already liked the methods that they had in place for ripping the test tube out of the bag, so maybe this wasn't as needed as some of the other things. For the flip lid or the plug lid, they like this idea, but for them, it would be more of a price point rather than a time issue. And so they would want to get to know the price and materials better to make sure it would still uphold that seal and be cheap. For the drill, this was their biggest bottleneck in terms of screwing and unscrewing the caps, and they were actually already looking into making something like this. For the ring loader, they said this was another really big bottleneck for them, and it actually doesn't even need to be fully functioning to cut time for them, as long as all the test tubes could be properly oriented and like standing up and ready to be placed in. That's all they really need. And they've also now switched from 24 test tube rings to 48 test tube rings. So we would have to design for that going forward. Thank you.